Welcome to the cosmic edge of understanding, where today we're diving deep into one of the universe's most mind-bending mysteries, the black hole firewall paradox. Imagine being on the brink of a black hole, about to cross the event horizon. But is it really possible to cross, or does an unimaginable barrier await? Stay tuned as we unravel the enigma of crossing the event horizon. So, you're thinking of diving into a black hole? Great choice. If you pick a large enough black hole, you can cross the event horizon unscathed and delve into the mysteries of its core, before the central singularity wipes you out. That was the prevailing theory, at least. Nowadays, many leading physicists argue that avoiding severe paradoxes in fundamental physics might mean every black hole is wrapped in a layer of intense energy, blocking anything from crossing the event horizon. Sounds like science fiction? That's the bizarre nature of black holes for you. Today, we're going to explore why some of the brightest minds in physics are taking the idea of black hole firewalls so seriously. Einstein's general theory of relativity has been a game-changer in understanding space, time, and gravity. Its bold predictions, from time dilation and black holes to gravitational waves, have been proven time and again. It all began with what Einstein considered his happiest thought, a profound link between the sensation of free falling and floating in zero gravity. This insight, combined with the unchanging speed of light, laid the foundation for general relativity. Let's dive into these concepts and unravel the science behind them. In our recent episodes, we've unpacked the enigma of black holes, these cosmic giants that can either destroy or duplicate quantum information, challenging a core concept in quantum mechanics known as unitarity. Here's the gist. If black holes can engulf quantum information and then emit it as Hawking radiation, we end up with the same quantum information existing in two places at once, essentially breaking physics. But if we stop this information from falling into a black hole, we're messing with the equivalence principle. This principle assures us that nothing unusual should happen to any object passing through an event horizon, provided the black hole is large enough to prevent any noticeable tidal forces. We're stuck in a classic catch-22, violate unitarity or the equivalence principle. This dilemma is known as the black hole information paradox. One possible solution? The idea of qubit duplication might be acceptable, provided there's no observer or no conceivable reference frame that can detect both copies of the information simultaneously. This brings us to the concept of black hole complementarity. In a previous episode, we watched Alice and Bob's daring attempts to outwit the laws of physics and observe both the swallowed and the Hawking radiated qubit. But it turns out, reality is one step ahead, making it seemingly impossible for any observer to witness duplicate qubits. Enter a thrilling new thought experiment, conceived not long after our initial adventures with Alice and Bob. This experiment didn't just potentially expose quantum cloning, it also introduced the concept of a firewall, a blazing barrier of energy that blocks anything from entering a black hole at all. This radical idea preserves unitarity, but at a considerable cost. It completely shatters the equivalence principle. Many physicists are torn over this. The firewall argument is compellingly strong, yet it demands that we reconsider some fundamental aspects of what we understand about the universe. So, how did we find ourselves in this bewildering predicament of contradictory concepts? To get to the bottom of this, we need to revisit the black hole information paradox, not just through the lens of quantum information, but also through quantum entanglement. Quantum entanglement involves pairs of quantum objects so intimately linked that the state of one, no matter the distance, instantaneously affects its partner, with both existing in a superposition of multiple states. This eerie connection suggests that the fates of particles across cosmic distances are interlinked, challenging our deepest understandings of reality. Let's dive deeper into this quantum quagmire and unravel the mysteries of black hole firewalls and quantum entanglement. Now, let's zoom in on black holes and entanglement. The story begins with a groundbreaking discovery by Stephen Hawking and Jacob Bekenstein. which gave birth to the black hole information paradox. They found that as a black hole grows, so does its entropy. Think of entropy as a measure of all the hidden information within a system that we can't access. This growing black hole entropy suggests that the details about everything that has ever fallen into the black hole are lost to us. Most physicists believe this information must be encoded on the horizon and escape via Hawking radiation. Otherwise, it would vanish when the black hole eventually evaporates. The twist? The horizon's high entropy indicates that the degrees of freedom there are massively entangled. This means the quantum details about the original states of particles before they fell in are scrambled across the horizon. Initially, when Hawking radiation starts leaking out, it carries barely any information about what fell in, because it's so entangled with other particles on the horizon. However, as more radiation particles escape, intriguing patterns begin to emerge. Gradually, the information about the original material could, in theory, be pieced back together from the Hawking radiation. This reconstruction becomes feasible only when the radiation particles aren't solely tangled up with the now inaccessible horizon. Let's explore how these tiny particles might hold the secrets to unlocking the mysteries of what falls into black holes. As a black hole emits Hawking radiation, a transformation unfolds. Initially, each bit of radiation, each qubit, is deeply entangled with the particles remaining on the black hole's horizon. But there comes a crucial turning point, known as the page time, occurring when about half of the black hole's mass has evaporated. Interestingly, this point arrives at roughly 90% of the timeline towards the black hole's complete evaporation. It's at this moment that the entanglement between the remaining black hole and the expanding cloud of Hawking radiation peaks. From here, the entanglement entropy begins to decrease, and it becomes increasingly feasible to identify and decode the entangled pairs of Hawking qubits. Imagine a single qubit, still clinging to the horizon around the page time, deeply entangled with a far-flung particle of Hawking radiation. It's almost as if this horizon-bound qubit yearns to reunite with its quantum sibling, transforming into Hawking radiation itself. Let's delve into how Hawking radiation works in a more tangible way. Picture this. In the vacuum of space, pairs of matter and antimatter particles are continually popping into existence and then annihilating each other. Near a black hole's event horizon, this fleeting dance takes a dramatic turn. One particle might get trapped by the black hole, allowing its partner to escape. This escapee becomes a real particle of Hawking radiation. For those keen on a deeper dive, we've covered this in episodes framed around quantum field theory. There, we describe the space vacuum as a dynamic balance of positive and negative particles, constantly interacting in a cosmic ballet. Stay tuned to explore more about how these fundamental processes shape our universe. Here's the fascinating part. Every time a black hole swallows one of these particles, its partner escapes as Hawking radiation. These pairs must be entangled with each other, a concept so fundamental that some argue it's what stitches the very fabric of space together. The entanglement of these quantum fluctuations is crucial. Without it, there might be no space as we know it. Now, let's get back to our qubit perched at the horizon, ready to become part of the Hawking radiation. This qubit is in a unique position. It's entangled with a distant qubit already in the Hawking cloud, but it also needs to be entangled with an adjacent qubit just below the horizon. Without this second entanglement, it can't sacrifice a partner particle to the black hole to make its escape. Here's where it gets even more intriguing. Our qubit is entangled with both the Hawking cloud and the black hole's interior, a double entanglement. You might think of it as quite promiscuous in its quantum connections. But quantum mechanics has strict rules about this sort of thing. In particular, there's a principle called the monogamy of entanglement. It states that if two particles are maximally entangled with each other, they can't be entangled with anything else. So, to prevent our black hole from being over-entangled, we need to break one of these connections. Since the entanglement in the Hawking radiation is what we want to preserve, it holds crucial information. It's better to break the entanglement between qubits above and below the horizon. But breaking entanglement comes with a hefty energy cost. Calculations show that severing the entanglement between swallowed and radiated particles at the horizon requires a massive amount of energy. In fact, to break all these entanglement connections, there would need to be an incredibly intense energy screen just above the horizon, so powerful that nothing could cross it without being completely thermalized. This energy screen is known as a firewall. The firewall concept has two major benefits. It resolves the unitarity violation by ensuring information isn't duplicated and maintains the integrity of quantum mechanics. So, while it might seem like a drastic measure, the firewall is a crucial element in our quest to understand the enigmatic nature of black holes and the quantum world. From a distance, you wouldn't even notice the firewall. The extreme gravitational redshift of radiation coming from just a tiny Planck length above the horizon turns it into faint, Hawking radiation. So while firewalls might ruin our adventurous dive into a black hole, they serve an essential purpose. However, there's a catch. The firewall hypothesis clashes with the equivalence principle, the cherished idea we started with. The equivalence principle formally states that there's no experiment you can perform in a small patch of space-time to distinguish between freefall and floating in zero gravity, or between standing still in a gravitational field with a specific g-force and accelerating without gravity at the same g-force. If Alice is free-falling towards an event horizon, the equivalence principle dictates that she should experience a quantum vacuum consistent with empty space and see no local sign of anything unusual. But a firewall would violate this principle, as she would encounter intense radiation instead. So, while firewalls are an intriguing solution to some of the paradoxes in black hole physics, they force us to reconsider some of our most fundamental principles. Stay tuned as we continue to explore these cosmic enigmas and how they might reshape our understanding of the universe. The black hole firewall paradox is a more refined version of the black hole information paradox, introduced by physicists Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully in 2012. Hence, it's also known as the AMPS paradox. The existence of firewalls is still debated among physicists, but the crucial point of the AMPS paper is that the black hole information paradox remains unsolved. Specifically, black hole complementarity doesn't fully address it. As we discussed in our previous episode, black hole complementarity suggests that quantum cloning isn't a problem because no observer can detect it. However, the firewall paradox provides a loophole. Alice could descend close to the event horizon to check for a firewall. If she finds one, the equivalence principle is violated, which is a major problem. If she doesn't find one, she can infer that quantum entanglement exists across the event horizon. Then, if she backs out, she'll see that this entanglement also exists between the horizon and past Hawking radiation, indicating a violation of the monogamy of entanglement and unitarity, which is also a major problem. The power of the firewall argument lies in Alice's ability to determine whether the exterior and interior of the black hole are entangled without actually entering the black hole. This undermines the main benefit of black hole complementarity, even though complementarity still seems necessary for other aspects of black hole physics. So, what does this all mean? Well, it's still an open question. Some, including the AMPS quartet, argue that breaking the equivalence principle is less drastic than breaking unitarity, so they lean towards the firewall solution. However, breaking the equivalence principle is radical enough for many who prefer a solution that doesn't violate either principle. Leonard Susskind and Raphael Bosso, for instance, suggest we might need to rethink the theories we use to describe events above the event horizon. If we don't want to break unitarity or the equivalence principle, we must consider that our current theories, like quantum field theory, QFT, might be flawed in these extreme conditions. This is the same QFT that works perfectly well in less extreme situations, similar to the event horizon of a large black hole. There are also some wild ideas out there. For example, Gary Horowitz and Juan Maldacena propose reframing quantum field theory to include both forward and backward causal directions. This might offer a way to reconcile these paradoxes without breaking our fundamental principles. Alternatively, a complete theory of quantum gravity might save us from information swallowing black holes. Take the fuzzballs of string theory, for instance. These propose that matter unravels into massive balls of elementary strings below the event horizon. This process allows quantum information to move back into the universe, again bypassing the need for a firewall. In essence, the black hole firewall paradox reveals that our current understanding of black holes is incomplete. Many physicists believe that resolving this paradox could be the key to a deeper theory that unites quantum mechanics and general relativity. This could even lead us to explore how space itself emerges from quantum entanglement and how unraveling that entanglement could create firewalls at the edge of space-time. Now, let's switch gears for a moment. 12 years ago, on July 4th, 2012, the ATLAS and CMS collaborations announced the discovery of a new particle to a packed auditorium at CERN. It was the Higgs boson, the particle that makes the existence of matter and interactions as we know them possible. To celebrate the fireworks of that collision, we've designed our very own limited edition merch. Black holes are regions in space where the gravitational pull is so strong that not even light can escape from them. At the heart of a black hole is what we call the singularity, a point where all laws of physics as we know them cease to exist. Surrounding the singularity is the event horizon, the so-called point of no return. Today we're focusing on this very boundary and the paradox it presents. The firewall paradox arises from a conflict between quantum mechanics and general relativity. According to Einstein, crossing the event horizon should be uneventful, with nothing particularly dramatic happening at this boundary. However, quantum mechanics introduces a different story, suggesting the existence of a firewall that would incinerate anything that dares to cross the event horizon. The scientific community is deeply divided on this issue. Some theorists suggest that the firewall is an inevitable conclusion of quantum mechanics, designed to resolve the information paradox, another black hole conundrum concerning information loss. Others argue that such a firewall contradicts Einstein's theory of relativity, which governs our understanding of gravity. If the firewall exists, it would rewrite the rules of physics as we know them. This has profound implications, not only for our understanding of black holes, but also for the fundamental principles of the universe. It challenges the smooth fabric of space-time postulated by relativity, introducing a discontinuity that quantum mechanics struggles to explain. Currently, it is beyond our reach to test these theories directly. Black holes are far too distant and their conditions too extreme for direct observation. However, advancements in astrophysics, such as the Event Horizon Telescope, are pushing the boundaries of what we can observe and test, bringing us closer to understanding whether the firewall truly exists. Stephen Hawking introduced the concept of Hawking radiation in the 1970s, which posits that black holes can emit radiation due to quantum effects near the event horizon. This radiation causes black holes to lose mass and energy over time, potentially leading to their evaporation. The existence of Hawking radiation adds another layer to the firewall paradox, raising questions about the fate of information and the true nature of the event horizon. The information paradox is a fundamental issue in black hole physics. It questions whether information that falls into a black hole is lost forever or somehow preserved. According to quantum mechanics, information cannot be destroyed, yet black holes seem to obliterate it. The firewall paradox offers a potential resolution by suggesting that information is radiated away, but this clashes with the smooth experience predicted by relativity. Quantum entanglement is a phenomenon where particles become linked, such that the state of one particle instantaneously influences the state of another, no matter the distance. The firewall paradox posits that entanglement could be disrupted at the event horizon, creating a high-energy barrier. This disruption would prevent the smooth crossing of the event horizon and challenge our understanding of quantum entanglement. Einstein's equivalence principle states that the laws of physics are the same for all observers, regardless of their location or velocity. This principle suggests that an observer crossing the event horizon would not notice anything unusual. However, the firewall paradox directly challenges this principle, proposing a violent encounter at the event horizon, thus questioning the very foundations of general relativity. Several alternative theories attempt to resolve the firewall paradox without invoking a literal firewall. One such theory is the fuzzball concept, which suggests that black holes are not smooth, featureless entities, but rather complex, tangled masses of strings. Another theory proposes that the event horizon is not a sharp boundary, but a gradual transition, allowing for a more seamless crossing. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together, we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.